So walking around, I had an interesting follow-up question from the previous problem we did. In the previous problem we did, I think we started off with a picture that looked like this. So we had some positive charges, some negative charges. We looked at the electric field. We concluded that the electric field kind of pointed off in this direction here. We didn't spend the necessary time to actually calculate the magnitude of the field. I kind of waved my hands a bit. But we said we had a non-zero electric field. It's pointing off in that direction. But when I summed up the voltages, K, Q over R, well, I've got just as many positive voltages as I have negative voltages. So my voltage was equal to 0. So somebody asked the question, hey, that's kind of interesting. Your voltage is equal to 0 even though your electric field is not equal to 0. Is that allowed? Is that common? Well, we can see it, so therefore it must be allowed. Is it common? Well, I guess that depends upon your idea of common. Okay? The other question you could ask is, hey, if my electric field is 0, is V equal to 0? Okay? And here we'd have to go and think about the relationship between my electric field and my voltage. You say, okay, well, we've already written this down. Delta V is equal to minus E dot ds. What I'm going to do here is I'm going to actually rewrite this a little bit. Okay? And you say, well, why are you going to do that? And I say, well, sometimes integrals make people kind of freaked out. I'm going to go in the opposite direction, okay? I'm going to take the derivative of both sides. Say, okay, that sounds good. Take the derivative of both sides. Well, I'm going to take the derivative of delta V. That gives me dV ds. And then I'm going to pull over that minus sign, and I'm going to say that's equal to E. Okay? Now, if you know a little bit more fancy math, you can say, well, wait a minute. I'm a little concerned because I know that electricity is the electric field is a vector. How are you pulling a vector out of this? If you're being very careful and you're doing the math properly, what you're doing is you're taking partial derivatives here. So dV dx is equal to E in the x direction. dV dy is equal to E in the y direction, and dV dz is equal to E in the z direction. You say, how come your d's turned into 2's? It's because I'm not very good at drawing the partial derivative sign. Okay? If you aren't familiar with partial derivatives, I think I'm going to say don't worry too much about that. Okay? I'm not going to give you something challenging on a test that would put you in a position where not seeing that in a math class puts you in a bad place. But I want you to understand that the relationship between an electric field and a voltage, because in one direction it's an integral, in the other direction it's a derivative. So a lot of times people will say, okay, well, I can use this whole voltage idea if I'm trying to figure out energies, like we just did in the previous problem. Voltages are also really, really powerful because sometimes it's not that hard to calculate a voltage. Okay? That was the entire point of our first exercise. Voltages a lot of times are easier than fields. But what we're learning here is that if I can calculate a voltage, I am basically a derivative away from figuring out my field. So sometimes you look at something and say, oh, figuring out that field might be nasty and ugly and hard. If you can figure out the electric potential, if you can figure out the voltage much, much easier, do that, take a derivative, and there's your field. Okay? Now you're saying, well, I seem to think this is interesting, but it's really kind of drawn us away from our original question, which is, hey, when V is equal to 0, how come we can have a non-zero electric field? And when E is equal to 0, is V necessarily 0? I did this because I wanted to just basically hone in on this relationship, that our electric field is the derivative of the voltage. Okay? I know something else. I can go all the way back to physics 4a. Now, in this case, we've got too many v's, so I'm just going to write out velocity. Velocity, you know what that is? That's the derivative of the position, right? Okay, hopefully you're nodding your head. If you're not nodding your head, then we're kind of in trouble. Yes, I remember that from Physics 4a. Okay? Hey, if my velocity is equal to 0, does that mean I'm at x equals 0? No. Hey, if I'm at x equals 0, does that mean my velocity is equal to 0? No. Okay? So when you look at that way, you can say, okay, well, velocity is the derivative of position. Having a 0 velocity does not force my position to be 0. Having a 0 position does not force my velocity to be 0. We can just kind of step back and say, okay, well, once we understand this relationship and this relationship, we can say, hey, when I have got a 0 electric field, that does not mean my voltage is equal to 0. When I've got a 0 voltage, that does not mean my electric field is equal to 0. Okay? Because these are just questions about the slope and its function. Okay? Now, this is probably a good time to think about this whole idea of what goes on in a conductor. Okay? Let's talk about voltages in conductors. So, suppose I've got a point charge. And I've got a conductor. Radius A, radius B, and then of course we go out to infinity. Okay? Now, a lot of times on an exam I'll say, tell me what the voltage is in all regions of space, and that's a perfectly decent question. You say, okay, region 1, region 2, region 3. And a lot of people immediately write down, oh, in region 2 the electric field is equal to 0, therefore the voltage is equal to 0. Okay? We just went over why that's the exact wrong answer. Okay? Just because the electric field is equal to 0, that does not mean the voltage is equal to 0. You say, well, wait a minute. This problem kind of looks a little bit hard. Can you step back and do the simpler problem? Suppose there was no conductor at all. Suppose we just wanted to know what the voltage due to a point charge was. And my response would be, well, I kind of hope that everybody would have read that in the book. We had that nice old weekend there. But, hey, might as well do it. I'm in front of people and my voice is holding out. So we could say, what's the voltage due to a point charge? And you know, because we've been working at this in class beforehand, that the eventual answer is going to be KQ divided by R. Let's see why that is. Okay, well, I know that my voltage, my delta V, is equal to minus E dot dr. I do a dr in this case since we're integrating over the radius. And usually by assumption, we start off at infinity. Okay? Voltages are measured with respect to infinity, so your integral starts at infinity. And then we're going to go from infinity down to whatever radius that we think is important. Okay? So now we can look at this and we can say, well, if we're comparing to infinity, I'm just going to say that V is going to equal minus infinity down to R of K Q R squared dr. That's an R to the minus 2, which becomes an R to the minus 1, but not before we lose a R in there. So we get a KQ over R from infinity down to R, and then you get KQ over R. Okay? Because when you take KQ divided by infinity, that gets you to infinity. Okay? So this is the simpler problem. You'd say, how are we going to do the harder problem? Okay? Well, we can think about this. We can say, well, I'm going to sit down and I'm going to think about what Gauss's law tells me. What does Gauss's law tell me that the electric field inside the conductor is? Okay, inside the conductor right here, it's 0. Okay? What does Gauss's law tell me about the electric field in region 1? Turn to the person next to you and say, hey, if I had to do this on the last test, what would I do for region 1? How much charge is enclosed? Q. Does that change as I change R? No. Okay, so we know inside here, my electric field is KQ over R squared. Yeah, because it's a point charge. Okay? Hey, how about in region 3? Okay, well, in region 3, we have to do it a little bit harder. We have to say how much charge is enclosed. We've got this original charge right here. Let's pretend it's positive. Then what the conductor is going to do is it's going to draw in negative charge to the inner surface until it exactly cancels out the positive charge in the center. So the charge enclosed right now is equal to 0. That's why the electric field in the conductor is equal to 0. Of course, to balance out all this minus charge on the inner surface, we have to have positive charge on the outer surface. How much positive charge is on the outer surface? Yeah, exactly the same in the center. And you say, why? Because the inner surface has negative charge to exactly cancel out the stuff at the center. And since the conductor's got a net overall charge of 0, what's on the outer surface has to exactly cancel the negative charge on the inner surface. So if I were to draw a big Gaussian surface like this, the total charge enclosed is going to equal Q. And that doesn't matter what R is, so long as R is outside of everything. So my electric field outside of everything is going to be KQ over R squared, which is fine because that just looks like a point charge. So if I wanted to know the electric field of this situation, you'd say it's a point charge in the region in the hollow part of the conductor. When I'm in the body of the conductor, it's equal to 0. And when I'm outside of the conductor, it looks like a point charge field again. Okay? So now we turn around and say, well, let me figure out what my voltage is. You'd say, okay, well, that's always going to be sort of the same setup. Well, I need to be a little careful. So long as I don't have any charge at infinity, it'll be the same setup. I'll turn around and I'll say I'm comparing to a point at infinity. So the initial point in my integration is infinity. I go to R and I'm going to integrate E dot dr. Okay? You say, well, suppose I'm outside of everything. Well, if you're outside of everything, then I'd say your voltage in region 3 is going to equal minus infinity down to R of the electric field in region 3 dot dr. You say, okay, that makes sense. I'm just integrating against the field that's where I'm at. And say, okay, well, that's good old-fashioned KQ over R squared, dr, R hat, and with a little bit of math, KQ over R. And if you're kind of struggling with this sort of series of calculations, it's almost literally the first thing in the book that they calculate after doing a constant field. Okay? I guarantee you've seen this before if you read your way through your chapter. Okay? Then you say, well, what about region 2? What's the voltage in region 2? Well, I'd say you need to do the exact same thing. Let's set up an integral from infinity down to R of E dot dr. That's literally the definition. You say, okay, well, when I do this, this is kind of interesting because I have a piecewise continuous function. You're like, oh no, he's using words for math. This just means that when I'm in region 3, I've got an electric field which is appropriate for the electric field in region 3. And then when I move into region 2, I've got another electric field which is appropriate for region 2. So I'm going to draw this out. I'm going to say, well, from infinity down to the outside of my conductor, I have to deal with the electric field which is in region 3. And then from that border down to where my R is, I have to figure out what my electric field is in region 2. And I have to figure out what dr is, or what this integral is. Okay? Now, the beautiful thing about this is it looks intimidating, but it's actually not that bad, okay? So we can go and do this first integral, and it's going to be, well, kq divided by r, evaluated these two endpoints, okay? One of them is going to be kq divided by infinity, okay? That one goes away. The other one is going to be kq divided by our upper limit, kq times b, okay? So that's the voltage that you would be if you walked your way all the way to the outer edge of that conducting sphere, okay? Then you say, oh, well, I have to subtract off this guy, br e2 dr. What's the electric field in region 2? 0. What happens when I integrate 0? 0. Beautiful. Okay? If your electric field in that region is equal to 0, then your change in voltage will be 0. That does not necessarily imply that your voltage is 0. Okay? If I've got 0 velocity, that means my change in position will be 0. That does not mean my position is 0. Okay? Take these things, map it back onto know what you know before, velocities, positions, accelerations. Think of it in those terms. Okay? Now you say, well, suppose I have to do one last step. And I say, yeah, suppose you do have to do one last step. Let's figure out the voltage in that final region inside that hollow, inside the conductor. Well, then I just have to integrate over 3 regions, B, E3, dr, with appropriate dot products and vector signs, from B down to A of E2 dr. Then finally, from that inner surface of that conductor all the way down to my point of interest. Here again we do the exact same things. Hey, you know what? I've already figured out this first integral. That's going to be kq divided by b. Then I'm going to subtract out 0. Then I'm going to have a term that looks like this. It's going to be kq divided by r minus kq divided by a when we go and do those integrals. Okay? Now, like a lot of times in this class, we've done a lot of math and we get an answer and we say, if only there were a way of making sure that that answer made sense and is the correct answer. Okay? Here's the way I would look at this and say, here's how I know, or at least suspect that this is the correct answer. Okay? In the limit where B approaches A, in other words, I take that thin shell of conductor, or thick shell of conductor possibly, and basically make it thinner and thinner and thinner. As B approaches A here, I recover the voltage that I would get if I had no conductor at all. Okay? So, looking through this, kind of a lot of math. First of all, I'm really hoping people have gone through the book, seen the sample problems, done a little bit of homework, and this is not frightening or confusing to them. They say, okay, we've done this. Okay? From there, I want to take the more general practice of understanding that voltage is always just going to be this integral. If we go back and do a Russian doll problem, the first thing we would do is we go and we would evaluate Gauss's law, work our way out. And with Gauss's law, we'd always start in the middle and work our way out because that made calculating Q enclosed very easy because you just take the Q enclosed from the last step and add on a new layer. Okay? Voltages in some sense are the exact opposite. You start from the outside and work your way in. You say, well, why is that? Kind of the same deal. Because if you do it in that direction, at each step, all you're going to do is you're going to add in one more term to your integral and build off of your previous answers. Okay? So that's a lot of talking, not enough practicing. So what I'm going to do is I'm going to stop this here.